Okay, folks, here we go. Diving into thermodynamics. Thermo meaning heat, dynamics meaning movement, heat movement. We're diving into some heat chemistry. Now, before this week, we didn't. Well, maybe you did care deep down inside, but we never concerned ourselves with calculating how much heat in a reaction was either given off or taken in. Oh, and that reminds me, heat given off, heat taken in. Let's go back to a little bit chemistry 1, where we learned a little bit about thermodynamics, not a lot, but we dived in just a bit about thermodynamic reactions, and those are called enthalpy. Enthalpy changes. Enthalpy, that's one of the things that we need to know in this unit. Enthalpy. And enthalpy means heat, either given off or taken in. It's the heat exchange in a chemical reaction. So enthalpy is an H, and we're also going to have to learn about entropy, similar but sounding but different, but very different. And that's entropy, and then we're also going to have to learn a little bit about delta G's, which are Gibbs energy. And again, we'll learn about these two. But for now, let's focus on this. Also, in the back of any chemistry book worth its salt, you're going to find an appendix, not a stomach, okay, not a small intestine, but an appendix, a little biology. We are going to find an appendix that has a table that will usually have all three of these things listed for particular elements, common elements and compounds that you would have in usual, typical chemical reactions, very common chemical reactions like the formation of carbon dioxide or the formation of water vapor. And these things have heats associated with them. 3 different columns. Let's focus on this one right here. Now, why do I put this little, what looks like a 0 up here? That means under standard conditions. So under standard conditions, somebody had to say, well, what about if it's like very low pressure and very high temperature? Is that going to kind of change some of these things? And the answer is yes. So under standard, somebody said, well, wait, time out. What are we going to list? Are we going to list them under, certain pressures and temperatures? And somebody said, I am going to say, yeah, let's do that. And let's agree that we will list them under standard conditions, which are 25 degrees Celsius, 25 degrees Celsius, about 77 degrees Fahrenheit, so a nice warm room, and 1 atmosphere of pressure. So this means under standard conditions of 25 degrees Celsius and 1 atmosphere of pressure, which is typical, it's usual lab conditions. Okay, unless you've got a very cold lab, you don't want that. You want a nice warm toasty lab, and that would be these conditions. Okay. So this one here, the delta H means enthalpy. I'll spell that out for you. Enthalpy. And enthalpy means your heat content or heat exchange in a chemical reaction. Many different kinds of chemical reactions, and when we have those chemical reactions, we either take in heat during the reaction or we have heat exiting the reaction. Exothermic meaning exiting, endothermic means entering, and in X, so the prefixes means in and out. Okay, so when we have a reaction that's endothermic, it might be something like this. Compound A plus compound B plus heat make compound C and compound D. This heat is a reactant. When heat is a reactant, is endothermic. When heat is a product, so let's say we've got compound A plus compound B, making compound C plus compound D, and heat. Heat is now a product, that is exothermic. So endothermic, heat is a reactant. Exothermic, heat is a product. All right, so now that means heat can be exchanged, taken in from the environment to have the reaction do its thing, or heat can be produced into the environment, spread out into the environment when the reaction happens. This, by far and away, is the most common of our reactions in nature. You're going to have exothermic reactions. And a quick reason for that is that when heat is given off, energy is released. And things which are very energetic, if they give off some energy, they calm down. Calm. If you give off energy, you go from a higher state of energetic state to a lower energetic state, and nature likes that. Nature likes things to be calm. Yo, chill, man, chill, relax. Okay, that's good, nature like that. So usually, we're going to have exothermic reactions. Compounds actually will do their thing and become more stable. And becoming more stable, they give out that excess energy as an exothermic reaction. So very important reactions in society are exothermic. That's you driving your automobile. Okay, you have gasoline. Boom. That's a combustion reaction. And that combustion reaction releases a lot of heat. You know that. I mean, put your hand on the tailpipe. Yeah, go ahead, do it. Try it. You won't. No, don't do that. Don't do that. I'll get in trouble because you'll say, it was my fault that you burned your hand. Don't do that. But it gives off a lot of energy. We use oil and natural gas, natural gas in the house to heat our homes, and those reactions give off a lot of heat. We want that heat. So a lot of times these exothermic reactions are very important to society. There's a lot more different exothermic reactions out there. Okay, so anyways, reactions will have heat of a reaction. This heat of a reaction change. So a change in the heat of a reaction, and those can be exothermic or endothermic. So you can have exo or endothermic reaction heat changes. All right, so that's what the delta means, change in the heat, enthalpy, change in the heat content of a reaction. And as I said, repeated one more time, that exothermic usually is the way that nature goes. All right, well, how are we going to figure out these heats of reactions? How are we going to determine it? I mean, if I want to know the change in the heat of a reaction, that means I'm going to have an idea of the heat content before the reaction. And I'll have to be able to do something. And remember, in order to get a change in something, you subtract, right? You subtract to get a change. If the temperature out today is 62, but yesterday was 45, what's the change? Okay, we do subtract those two numbers, we get our answer. So to get a change in the heat of a reaction, we're going to subtract change in the heat of a reaction. What we're going to do is we're going to subtract the heat. Now, I'm going to use a symbol. Sometimes you'll see it written like this. Kind of looks like an E backwards. Well, no, it means the sum of. And sometimes you'll see it written like this. Okay, it means the sum of. It's not a backwards E, actually, it's a forwards E. My brain's backwards today. So we have a, it kind of looks like an E, right? I mean, it's kind of, okay, but it's not an E. It just means the sum of. So a symbol means the sum of. You can make it either this way or this way. That's harder for me to use it the other way. The sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Okay, this is on the equation sheet which I had sent you. I just sent that actually the other day, so hopefully you see that now, the equation sheet that we have for this last section of the course. And it has this on here. It has the delta H of a reaction. The heat change of a reaction is going to be equal to the sum of the heats of formation of the products minus the heats of formation of the reactants. So to get a change, you subtract, and that's what we're doing. We're subtracting. We're subtracting the products minus reactants. Remember, in all the stuff that we've done in chemistry this semester, it's always like products first, right? Products over reactants. We're doing our K values and all that stuff. So products minus reactants this time, not over, minus reactants. But what is this? What is this delta F? I mean, you were talking about enthalpy and endothermic and exothermic reaction and the heat of a reaction. We want to know if the reaction is exo or endothermic. What's that? What's that heat of formation? Okay, well, as I said, in the back of a chemistry book and your chemistry book, I mean, some chemistry books, some like high school chemistry books, might not have tables of this stuff in the back. They might have a chart somewhere in the book, a smaller chart with delta H's, or H of formations of some common compounds and elements. But yours does have a whole list of what's called heats of formation at standard conditions. And if we look these up, we'll see some common things like maybe calcium. Calcium at 25 degrees standard conditions is a solid. And we're going to see a 0 for that. We're going to see hydrogen gas. Going to be a 0 for that, because that's what hydrogen is at room temperature, standard conditions, and standard pressure. So standard pressure, standard temperature, hydrogen gas is going to have a 0 value. Well, why is that? And well, some other things like oxygen are going to have a 0. But if you find something like carbon dioxide on that table, okay, it's not going to have a 0. Carbon dioxide, if I remember right, it's like negative 394 or something like that. I'll write that down. I think that's right. Negative 394. And these are in kilojoules. These are a certain amount of heat kilojoules per mole. So what this is, you're going to find these labeled as kilojoules per mole. Now, kilojoules is a heat unit. Per mole is an amount. So this means that we'll have a change in heat of negative 394 when carbon dioxide is formed. That's what the F means. It means the heat of formation. So when carbon dioxide is formed from its basic elements, like carbon and oxygen, you're going to have a negative 394 heat change. Well, why negative? That means it's an exothermic reaction. Exothermic has a negative heat of reaction. So because it's exo, it's giving off. It's losing, the reaction shows a loss of 394 kilojoules per mole of carbon dioxide formed. Then we end up having a negative because it's given up and lost to the environment. If it's an endothermic reaction, you will see a positive in front of its heat of formation value. So positive values mean they're exothermic, negative values, endothermic, I said that right? Endothermic, and exothermic is a negative value in front of the number. And these are the amount of heat that's either given off, usually given off, sometimes taken in when something forms. All right, well, what's the deal with these having zeros? Why do those have zeros then? Because when we're not forming the calcium here, it's not a compound, it's an element. So it was decided that the values for elements in their state, their normal state at that particular temperature, 25 degrees in 1 atmosphere, standard lab conditions, that those elements are going to have a value for heats of 0. Now that's arbitrarily assigned, but that it'll make some sense. Hopefully, let me give you an example to compare it to. An analogy would be elevation. Sea level has been decided by everybody around the world, unless you're a rebel, don't be a rebel. Woo-hoo. That sea level is the way we measure our elevation. You're either like 250 feet above sea level, or you can be 250 feet below sea level. You're a positive above sea level or a negative below sea level. But sea level is decided upon. We could have made elevations, people could have made elevations at the deepest part of the ocean trench, in the Mariana Trench, the deepest part of the ocean, it's like negative 30,000 feet. But somebody could have said, no, we're going to start there. That's where we're going to have our 0 value at the bottom of the ocean trench, and everything will be measured above that, which means we'd be in Manchester, like, 31,000 feet above that point. But it didn't make any sense to people, so somebody said, no, that's stupid. Let's just make it at sea level as our 0 point. Well, somebody decided that 0 was going to be the starting point for our heats of formations for regular, the common shape, the common form of elements at that particular temperature, which is room temperature. And these are the forms, the states that these atoms, these elements are in at that temperature. So that was decided to be the 0 point. Okay, so diving in. Okay, let's take a look at the first question from the problem sheet for this week. And you got them out, right? You got those. Here they are. Okay, you got those. Okay, here we got our practice problems and our topics covered. Our topics covered actually go right along with the practice problems this week. There's a lot of problem solving. So let's just dive into problem number 1. Problem number 1 says, predict the value of the delta HF. Predict the value of the delta HF greater than, less than, or equal to 0 for these elements at 25 degrees Celsius. Now remember, 25 degrees are standard, it's a standard temperature, standard conditions. So we're going to make a prediction now for the elements bromine and iodine at 25 degrees. What will their H values be? Bromine here for A is is listed as a gas, and it's listed as a liquid. Okay, now, under normal conditions, normal atmosphere, normal 25 degrees standard conditions, what is bromine? What is bromine? Is it a gas? Is it a solid? Is it a liquid? I'm not sure. Well, check your periodic table. Find out. Get yourself one of these bad Larrys right here. You have one. I gave you one. And find bromine and see what it is. Hey, look, it's the same shade as mercury at room temperature, 25 degrees Celsius. That means it's a liquid. Bromine is a liquid under standard conditions. That is the common state of the element bromine under standard conditions. Now, by definition, that's given as a 0 heat content, a heat of formation. So this one gets the 0. That means if I find bromine gas in a column of H's listed somewhere, it isn't going to be 0. It's going to be more than 0. Okay, 0 is where we start, and then we go above that. So bromine gas is not what bromine is under standard conditions. It's not a gas, it's a liquid. So the liquid gets the 0. This is going to get something greater than that 0. All right. B, we have iodine. The iodine gas. No, actually, I think I put down as a liquid. No, gas. Gas and the iodine solid. Iodine solid. So, solid. Okay. So which of these two would we look up in the column and find as being a 0 for heat content, or heat of formation? I keep saying heat content. I mean, heat content is... All right, so heat of formation. Which one of these is going to have a 0? So in other words, what is iodine? What state is it in under standard conditions? Room temperature. What would you find iodine? Most you go, well, it's going to be a liquid. Liquid, how come you didn't put the liquid down? Because I know what iodine is a liquid. I got a cut last week and I put some iodine on there, rubbed it on there, that iodine. Oh, wait a minute. That iodine is not a liquid, it was in water. That's correct. That's iodine solution you're talking about. But that means that the iodine was dissolved in the iodine solution to produce that iodine solution. So it was a solid. So it's solid. Iodine, under standard conditions, is a solid. This one gets the 0. Iodine gas. Iodine is not a gas under standard conditions. It's 25 degrees and in 1 atmosphere. It's a solid. So that means this one is going to get a value that's going to be greater than 0. And how are these values determined? They're determined experimentally. Sometimes this whole idea that we have or giving something an assignment of 0, we can just arbitrarily determine that, okay, you get the 0, you elements under standard conditions. Why can we, how do we know? I mean, iodine, if I had iodine solid, does that mean it has 0 heat? It has 0 heat content? The answer there is, well, no. Of course, it has heat content. Particles are moving around. They have kinetic energy, kinetic theory. So there's some heat there, but we don't know how much heat. But what we can do is we can measure if we put that into a reaction with something else and we form something. We form, like, for example, carbon and oxygen O2 from carbon dioxide. We can see there's a change in heat. All we care about is the change in heat. It doesn't matter, if we're talking about the change in temperature from day to day, it doesn't matter if the temperature was 0 one day and 10 the next day. It's a change of 10. Well, what about if the temperatures were 80 and it went to 90? What's the change? Change of 10. What we're talking about is the change in the values, and so we just want to know what that number is. And so if we can take, like, we set the 0 values as 0, and we can then go from there and figure out what the change is. Does that mean they have 0 heat? No, it doesn't mean that at all. We're just interested in the change. Okay, so we can give something a starting point of 0, these elements, and we can determine what the change is through calorimetry when these reactions happen, and that's what we are concerned about. Okay, so I think this video has been going on for a long time. I've been making like an ancient city and babbling on for almost 20 minutes. That's long. It's going to take a long time to load this up. So we're going to stop with this video here, and we'll move on to the next problems in the next one.